Good afternoon. My name is Jacopo Querci. I'm a PhD in molecular biology and I'm a nutritionist and coach for extreme sport. This year World Championship at AIDA in France has been characterized by a number of deep and shallow water blackout. Also by in sometimes the best world freedivers. I would like to explain for a metabolic and molecular point of view what might have happened in order to give some ideas and for discussion forum and try to be safer in such demanding competition in this extreme environment. After immersion of the body within 6 heartbeat, the body change and there is a redistribution of blood to the brain, which occurs quite fast. That can increase the cerebral blood volume by up to approximately 700 milliliter. The increase in intrathoracic blood volume engorges the pulmonary capillaries and compete with air for space in the lungs, result in a 30-50% reduction in static and dynamic lung compliance. Whereas pulmonary gas flow resistance is increased by from 30 to 58% and impedance to 90%. The increase in pulmonary capillary blood volume seen on immersion in a 34 degrees environment, water, as a result of an increase of hydrostatic pressure, is not significantly increased. Instead, immersion at 15 degrees, something happened, suggesting that cold-induced vasoconstriction does not augment the blood volume shift caused by hydrostatic pressure. In conjunction with the increase in hydrostatic pressure on the chest, the hemodynamic alteration results in a 65% increase in the work of breathing. Vital capacity is reduced by an average of 6%, maximum voluntary ventilation by a number of approximately 15%, and expiratory reserve volume is decreased by an average of 60%. Which results in a reduction in functional residual capacity of the person who is in the water. Immersion of an unprotected body in cold water produces a large and fast fall in skin temperature, which in turn evokes the initial responsive to cold immersion, given the generic name of cold shock. The responses reaches a peak approximately within a 30 second of immersion, and there is a form of physiological adaptation within 3 minutes of immersion in most individuals. The inspiratory gasp occur almost immediately upon immersion. Unfortunately, this cannot happen during breath holding, complicating the physiology of immersion. During deep diving. This shift plus the large afferent neurological drive to breathe is probably responsible for the sensation of dyspnea experienced sometimes by the diver, rather than a bronchoconstriction or altered lung mechanism. The cold shock response can reduce maximum breath hold time between a range of 20 to 30% during the immersion, like Cooper et al. Has reported. For example, he reported that hyperventilation on cold water immersion occurs without an alteration in the sensitivity of the central chemoreceptor, so there is no interaction on the partial pressure of oxygen and CO2 level. The initial respiratory response to immersion in cold water occurs before there has been any change in core temperature, and the speed of the response in a certain way indicates that that there is a neurogenic origin, that the responses are not seen on immersion in warm water, for example, suggests that they are initiated by the cutaneous cold receptor, the superficial subepidermal location of which, approximate at 0.12 millimeter, explains the speed of the response and the fact that it is not influenced by subcutaneous fat thickness. Whether you are a fat or skinny diver does not matter. It has been suggested that thermoafferent neurological connection from the peripheral cold receptor directly stimulate the respiratory center, which during apnea are stimulated more normal and can alter the energy system response. Some scientists have demonstrated that middle cerebral artery blood flow is reduced during cold water immersion at 12 degrees. Compare, for example, with what is recorded in a water temperature at 35. In other words, the cerebral blood flow velocity seems seen during cold shock are higher than what would be expected for a given level of arterial carbon dioxide concentration, suggesting of either increased cerebral neurogenic activity, which is coupled with a demand of blood in the brain, induced by the sympathetic connection, and also hypertension. As already discussed, breath hold times are markedly reduced despite subject best effort to maintain apnea volitionally in cold water. This was accompanied by also tachycardia, and after the break of breath holding water, a profound hyperventilation and hypocapnia occurs, indicative of a powerful, again, sympathetic overdrive due to cold water. What can we do to go still deep and safer then, we might ask? Well, some scientists using a repeated immersion conducted over a short time period between 1 to 10 minutes on the same day resulted in a decrease in the response to the cold water from a physiological point of view. During the first 30 seconds of immersion, especially, which means that it is possible to do a cold acclimatization, although this is lost also quite fast. What about face immersion in cold water in, for example, 13 degrees, few minutes before immersion, to mentally and physiologically prepare the sympathetic drive before reaching the thermocline? Could this be a protocol to adapt for deep dive in the Mediterranean, for example? One experiment in particular has proved that training on the psychological skill, such as arousal regulation, mental imagery, had influenced the respiratory but not the cardiac component of the cold shock response. The obvious difference between the two, between the degree to which they are under conscious control, actually happen to be the case probably. Breath holding requires the voluntary suppression of a drive to breathe. In cold water, this drive comes from the cutaneous cold receptor. It is most likely that the psychological skill might improve the ability of subject to volitionally suppress the cold evoked drive to breathe and maintain voluntary apnea for longer. Well, this implies an enhancement of the descending inhibitory cortical pathway to the respiratory center, probably. The initial respiratory response to immersion in cold water can be habituated in a certain way. As few as 3 minutes immersion in cold water can reduce these responses by 50%, some scientific science has proven, with the response still being reduced by 25% 15 minutes later. This means probably that few days of cold water adaptation are not sufficient for minimize physiological reaction to cold water, especially in deep free diving. The anticipation, anxiety, and cold cutaneous stimulation leading to a sympathetic overdrive and tachycardia connected to it can influence the result of the dive. It seems that the vaguely mediated triad of responses to trigeminal nerve stimulation, such as apnea, bradycardia, and selective vasoconstriction, that constitute the oxygen conserving effect of diving response, are not responsive in cold water, especially when the thermocline arrive so fast with 1 meter per second descent. This means that the protection with oxygen conserving effect might actually be reduced, not only at the neural level, but also at the cellular level, especially in the most important critical phase of the dive, the ascent. Thank you very much.